Welcome to our last lesson of grade 12 pre-cal, lesson 9 of unit 7. So we're looking at what's called natural logarithms. So nothing that we are going to do is actually very different in this lesson in terms of any of the math that we've been doing, any of the graphing that we've been doing. There's only one difference, and it's that we're changing the base that we're working within. So things are going to look ever so slightly different. We're going to introduce some different letters into the process. But otherwise, don't worry, nothing actually new in terms of approach is happening here. So any positive number not equal to 1 can be the base for our logs. So we've played around with base 2, base 4, base 7, and gone from there. And basically anything to the power of what this is will give us our value. So we've got lots of flexibilities with what we can do with with our log system. And the common log, the one that we've been writing as just log without anything here, we've been treating as a base 10, and that's been working really well. But there are such things as what are called the natural logarithm. So again, common logarithm is base 10. All of these other bases we have to specify. So base 2 is 2, base 4 is 4, base 7 is 7. Okay, but the natural logarithm is base e. And you're like, what? Okay, e is kind of like pi. It comes from calculus. That's where we're going to pull it from. Okay, and we treat it as a specific value. Okay, so if you go onto your calculator, you should see a button that says ln. This is the natural log. And you might hear some people call it ln. Okay, in terms of reading it, but that is kind of it. So what it means is, and we see this in our first example, log base e. So again, e represents a number, and if we punch in the second function ln button on our calculator and put it to the power of 1, we get this value. So this is e, except it keeps going forever. Actually, it's 2. So if I write the one that I get on my calculator exactly, it's 2.718281828, and it keeps going. From there, I need to use a different button, and that's that ln or ln button on my calculator, instead of typing it in as base e. So if you take a second right now, make sure you can find that button on your calculator so that you know kind of how to use it and where it is, because we are going to need to use it on our test, on the exam, and more importantly, or more pressingly rather, in these questions. So find the button, and you should be able to type in just ln 5.36, and you should get a value. I get 1.67896, and you should get the same thing. I did round it off. It says 3975 on my calculator screen. Depending on the calculator, you might get more or fewer digits than that, but those should be the first decimal places. Okay, so you should try the next two. Okay, so for this one, we get a negative value, and for this last one, that's kind of the odd one out, we get ln e equals 1. And so this is going to be something that you're going to want to kind of like maybe make a mental note of. And the reason that we need to make a mental note of that is kind of, we're going to look to eliminate this piece as much as possible when we're working with equations, when it's possible. So why does this happen? Well, remember, if we go back to this notation, that this is the same as saying log base e of e. And in order for e to equal itself, it needs to be to the power of 1. And so that is why it equals 1. So we can evaluate natural logs. We can solve natural logs just like we solved for other equations. So we can do the inverse of a natural log is e to the power of 4.1 equals x. And then I can punch that into my calculator. It should be the second function, or shift and then pressing your ln button will get you e to the power of, and then you can type in your exponent. I get 60.34029. Okay. Same thing happens here. My base that's not written is e to the power of 0.89 equals x, and so x equals, again, second function ln, or shift ln, should get me to that e to the power of, and that is 2.43513. With respect to graphing, again, we're working in the same idea. We're still working with exponential graphs. So I'm still going to expect my general shape to look like, oops, not that, but this. I'm still going to expect my horizontal asymptote at y equals 0. I'm still going to expect my intercept to be at 1 because I'm still putting it to the power of 0, and it doesn't matter what my base is. If my exponent is 0, the value is 1. Okay, and it's just that my next point on my x-axis at 1 would be instead at 1, and not like 2 or 4 or whatever my base might be, but it will be at 1 and e. Okay. Conversely, when we have that negative exponent, remembering that kind of functions as like our b value in our transformations unit, so that's going to be a horizontal reflection. And I'm going to shift it down 3. So instead of my horizontal asymptote being at y equals 0, it's going to be at y equals -3. And so all my points shift down 1. So this is going to shift down on the y-axis. Instead of at 1, it's going to be at -2. This point here is going to be not at e, but e minus 3, which will take me down here below my x-axis, and it's going to be on the other side. Okay, now because e is a set value, I can figure out what that will be. Or I can just identify it as e minus 3. So in terms of listing that point, I would list it as -1 and then e minus 3. And so that's how I would graph that. So again, shape stays the same as any other exponential function. It's just we need to work with that letter now instead. And bearing in mind that it's about, again, if we look back at the value, 2.7, that gives you a perspective on like about-ish where to put it on your graph in terms of putting it with whole number scale. Again, here we've got a vertical stretch. And we've got a horizontal shift. We're going to go left 1. Again, going back to that transformations unit. So with all this information, I know that my y-axis, my horizontal asymptote, rather, y equals 0, stays the same. Okay. But I'm going to have that imaginary axis at -1 instead. And instead of my intercept being at 1, I'm going to multiply it by 3. So it would be here. Okay. So this should be 3e, or about 3 times 6, or 3 times 2.7, which would be 9, which is way up there already. So when I draw this graph, again, making sure it's not looking like it's going to actually hit my axis. That would be my sketch there. And then I would erase that. Okay. Graphs of ln of x. Again, because ln is kind of like a subdivision of log, it's still going to match the general shape. So it's still the inverse function of our exponentials. So I would expect that intercept at x equals 1. Label my axes, okay? And from there, my next point would then be at 1, and instead of being at like 2, if I was doing with base 2, I'm going to put it at about 2.7-ish to represent e. I've got that vertical asymptote now at x equals 0. Otherwise, again, my shape hasn't changed because I'm still working within that umbrella of logs. It's just a very special case. So then this is a vertical reflection. Vertical translation, up 1. So I can imagine that I've shifted my axis up 1. Oops, it's a really ugly line. Okay, I would expect that point to then be here. But instead of my shape increasing over time, I would expect my shape to be decreasing because of that vertical reflection. So my next point would be over here at 2.7. My asymptote would still be at x equals 0. Okay, so we can always use those transformations to help us. This is going to stretch it. This is going to reflect it over y. So instead I'm working on the left-hand side of my graph, and my intercept instead of 1 is going to be doubled, and it will be, I'm going to go up to 6 here, just in terms of being able to fit a second point in. Okay, but because I have no shifting left or right or up or down, I have no movement in my quote imaginary axis, nor do I have movement in my actual asymptote. So when I go to graph this, instead of it being at 1, I would expect it to be at 2 for my x-intercept. And instead of it being at e and 1, I would expect it to be at negative 2e. Or, sorry, e and 2. I'd expect it to be at negative e times, oh, I'm so sorry. I'm getting all turned around here. This is where mapping notation comes into play. I can focus myself. So trying to do it in your head sounds great, but sometimes that doesn't work. So I'm going to flip my x values and they'll stay the same otherwise, but then I will double my y values. So 1 becomes negative 1. but e and 1 becomes negative e and 2. So we get kind of a wider curve going on here, vertical stretch. So again, if you get turned around, make a table of values, use mapping notation, do something to help yourself so that you're not second guessing every point you put on your graph like I was. Okay. All properties for expanding and condensing logs hold true to natural logarithms. So our lesson about product law and quotient law and exponent law still stayed the same. So I'm going to go in and I'm going to just note where I'm multiplying, where I'm dividing, and then my exponents so that I can break it all apart. So this whole thing would expand to be 3 ln x plus, and this is all in square brackets because it's all in the numerator, 4 ln x minus 2, all subtracted by ln of the square root of x minus 5. Now, you might be pausing here and being like, but Miss Conrad, I can rewrite this as an exponent. And that's 100% true, but I have no law to help me break apart subtraction, to break apart a difference. So this is going to have to stay together inside my natural log, which means I'm just going to leave it as it is, and I don't need to worry about that conversion. Conversely, I can work backwards. I'm going to identify my exponents as the numbers out in front. I think there's supposed to be a ln written in here. It accidentally got deleted somehow. Okay, so going through, we've got 4. Those are my exponents. I am going to multiply this together. And then I'm going to divide all of this. Okay, so I've got in my numerator, well, first I've got ln of x to the power of 4 times x squared minus 4 to the power of 3, all divided by x plus 5. The power of a half. And if you want to rewrite that as a square root, you totally can. There's nothing stopping you, but you do not have to. If you leave it as a fractional exponent, that is perfectly okay. So either of these are both correct. Okay, so I know this is feeling like a long lesson, or that I'm rushing through it, but I'm only rushing because I am confident that you already have these skills and you're just kind of needing to see them in the context of ln. If at any point you're like, I'm not quite sure, make sure you go back to the videos that we have for other lessons that actually talk about these concepts more in depth. Okay, so again, solving equations with ln. I can rewrite this as e to the 7 equals e to the 5, that common base approach. And if I can do a common base approach, I'm in a good place, and what I can do is that, or 5x, is that I can drop my bases, right? And we get 7 equals 5x, and divide by 5, x equals 7/5. And I'm done. So that one's nice and quick. This one looks a little bit more intimidating. So if I take, I'm not sure how I can get my bases to be exactly the same, so I'm going to take the ln of both sides, just like I did in the lesson where I couldn't get a common base. So that leaves me with ln of 2x plus 1 ln e equals ln of 4x. What's nice here is that this, we saw, equals 1. So it just kind of disappears and leaves us with ln of 2x plus 1 equals ln of 4x. I can then either drop my lns altogether and write 2x plus 1 equals 4x and go from there. That's perfectly acceptable. Or you can try and move it over, use our product laws, whichever one you want. I'm going to do it this way. First, but I'll also show you how to do it the other way. So if I didn't just drop my natural logs right away, because I had them on both sides and they were the only terms, and I moved this one onto the other side, set it equal to 0, and tried to solve for and isolate for x, what would end up happening is I would end up dividing here, but then anything to the power of 0 is 1, so I could set my value equal to 1, and then I end up rewriting 2x plus 1 equals 4x, just like I ended up with over here, but after a lot more work. So I prefer this way. If this makes more sense to you, you are welcome to do it. Whichever one kind of seems like the logical thing based on your understanding of lns and logs. Our last one, again, we can take the ln of both sides. We're going to bring that whole exponent out front. So we're going to have 3x plus 7 ln e equals ln of 6. Again, ln e eliminates to 1, which is why we have this option. And so now we've got 3x equals ln 6 minus 7, and then divide by 3. And we're left with x equals, and we punch this into our calculator. Make sure you follow BEDMAS, so ln of 6 minus 7 should give you negative 5.20824, and then I'm going to divide that by 3, so I should end up with a final solution of negative 1.73608. Okay. And that takes us up to our previous lesson that we just did, lesson 8, where we were applying this theory. So there is a law of natural growth and decay, where as things increase at specific rates, we can project how much we're going to end up with if they have like a certain shelf life or half-life. So that's what these examples are doing. They're using that equation to do exactly that. So example 8, the population of a bacteria culture is 20,000. Okay, so this is our starting value. You know what, I'll scroll up so I have that equation showing. Sorry. There we go. Okay, so this P is our initial amount, our principal amount. It is increasing at a rate of 0.37. And we are going to use 25 minutes as our time. Oops. Okay, so given all of that, how do we do this? Well, our new population is going to be 20,000 times e to the power of 0.037 times 25. And in this particular case, we just get to plug and chug, so that's kind of nice. So I type in 20,000, and then I'm going to go second function ln to get that e value, and then make sure that both 0.37 times 25 end up in my exponent. And so I should have a final result of 50,437 bacterium. Which really grosses me out because that's a whole lot of bacteria, like over double, in just 25 minutes. Okay, so original concentration in this example is reduced from 0.03 to 0.01. Okay, so this is my initial, so it's P. This is my final, so that's A. And this is my time. Find the rate and the concentration at 10 minutes. So first we need to find the rate, and then we're going to work forward from there. So step 1 is a rate. You get 0.01 equals 0.03 E R times 4. With that in mind, I need to get my variable out of here. There's no way I'm getting E to show up somehow out of this, so no common bases are possible, which means I need to use log on both sides, but instead of regular log, I'm going to use ln because E is present. So basically, if you're trying to decide log or ln, E is going to be your deciding factor. If there is an E, use ln. If there is not an E, it honestly doesn't really make a difference. So you could use either one. So I'm going to take ln 0.01 equals 4R. Oops. I'm taking the ln of all of this, so there's some product in there. Ln of 0.03 plus 4R ln E. And this equals 1. So I'm going to try and isolate R from here. So I've got ln of 0.01 divided by 0.03, because I would have ended up subtracting it over here and using my quotient law. And then I'm going to divide that all by 4. In doing that, got ln of 0.01 divided by 0.03 is negative 1.09861, and then I'd divide that by 4, gives me negative 0.27465. I'm also asked, because I have to go back to the question and make sure I've answered it, that I want to know the concentration in 10 minutes time. So I can interpret this in one of two ways. I would say in 10 minutes would mean I'm already at 0.03. Actually, I'm going to go with the other one. I'm going to keep this as my principal and ignore kind of these pieces but use my rate. So we're solving for A, 0.03 e to the power of, and now I have R, and time is 10 minutes. And again, I just need to plug and chug for this one. And so I end up with 0.001924 as my concentration.